All right, so we worked out this example. Maybe we did. Let's see. This is all the, I don't like to delete these slides. I'm like, oh, all this information exists. Why should I delete it? What would happen if if you designed the centrifuge so the arm could extend from 6 to 10 meters? So just think about this for a minute. If you had this centrifuge, remember we did the calculator, we did the problem solving for it to figure out the acceleration, the magnitude of the acceleration. And you know what this does is it gives you another degree of freedom, right? It lets you determine how quickly the acceleration in the gondola changes, right? So you could actually start. Let me show you the equation. Right, the radius term, right? This is the change in the radius with time, right? So this is the velocity of the arm. So if the arm could move, you could actually adjust this whole term. Now don't forget, you'd actually, the instantaneous acceleration at a given point would still be the same, right, at r. But you know, you could impart a velocity and an acceleration to those to that arm and change the overall acceleration. And this is just you know, how you might adjust the g onset rate. All right. Oh yeah, I added this. This is it's called supplemental problem because I added it at the end. Let's see. So here we've got this boom, right? These people on this. I don't know what that little cart is at the end of the boom. The cart. And it says the length of the boom, right? So this is one of these problems now where the length is changing. So the length is being decreased at a rate of 0.2 meters per second, right? So this is a changing radius. And the boom is being lowered at a constant rate of 0.08 radians per second. So determine the velocity of point B and the acceleration of point B. And we're going to determine that for this instant, right? At the instant where theta is 30 degrees, right? So it's being lowered at 0.08 radians per second. And this is pulling in at 0.2 meters per second. And at this particular instant, the theta is 30 degrees and the length is 6 meters. And we want to determine for B, what's the velocity and the acceleration of point B. So obviously we have to define our coordinate system, and choosing polar coordinates in this makes it, again, this is one of those problems where you're like, well, you know, it really makes sense to use polar coordinates. All right, so let me move over to the document camera. I thought I had more information here. What I did is I wrote these equations out from before. So why don't you guys write those down? Let's see, did I put the, yeah, check my dots. I'm not used to using the dot notation. Let's see, dot, double dot, one dot, one dot, one dot, one dot. Okay, so these are the two equations we're starting with for polar coordinates. And let's just look at this and let's write down what we know here. The first one, we're not going to use acceleration for part A, so we're going to look at the velocity equation. So for part A, we're going to look at this and say, okay, what do we know? This is a dot. These are not as clear on my screen as they are. Well, I mean, obviously I can see them better on paper than I can on the screen. The dots are like pixel size. All right, so we're going to start with looking at the velocity equation. And this is a vector, right? So we've got two components. We've got the r component and the theta component. And what are those? Let's see what we know. Well, we do know r dot, right? And that is 0.2 meters per second, but we have to define a direction. So we're going to define a direction as r is positive. And typically, let's see, which direction did I find my theta? Okay, I defined my theta as, oops, E and theta look so similar. That's an E. E theta is also positive. Going up like that. So these are the directions. So r dot is going to be equal to negative 0.2 meters per second, right? Because r is decreasing, right? That's 0.2 meters per second. And let's see. Oh, we're not anywhere. Double R. Oh, R is 6 meters, and I'm going to write this. So R is 6 meters. This is at this instant, right? I don't want to give you the impression R is constant here. I'm just reminding us that R is at that instant. And then theta is 0.08 radians per second. Sorry, this is not theta, this is theta dot. So this is r dot, we know that, right? We know r, and we know theta dot. Theta dot is negative 0.08 radians per second. Just for the next, well, let me work this out and then I'll talk about that. All right, so what do we got? We've got, we just plug this in here, and we've got v, the vector v, is equal to negative 0.2 ER. Here I can just multiply R, so 6 times negative 0.08 gives me a negative 0.48 E theta, right? And this is all in meters per second, right? Notice this is, let's look at the units on this. This is meters per second, right? This is a linear velocity or linear term. Well, yeah, this term here, R is linear, right? Theta is in radians per second, so this gives you the meters per second. So both these terms are meters per second. So this is your velocity. Again, this is fairly straightforward if you just start from the polar coordinate equations and look at the terms you have, or the terms you need, and then what information do you have, and work from there, right? And occasionally you might have to, do an integration or take a derivative. All right, so for part B, before we get to part B, I also want to point out here, because these are constant, right? Note R, the second derivative of R with respect to 0, or with respect to time, is 0. And I mean, this is basically the linear acceleration, right? Same thing with theta, right? The acceleration in both those directions is 0. And we're going to use this later on when we get to the acceleration term. So right now we can see we've got this term goes away, and this term goes away for acceleration. So for acceleration, it looks like we still need r theta dot, r dot theta dot. Let's look at acceleration and see what's going on here. I'm going to draw a little, well, we'll see what, let's see how well this comes out. Here's our point. That's point B, which I'll label. I'm not going to label now because if I label it, the label is going to be in the way. This is VR, right? V theta looks like this. And I'm going to have X and Y coordinates. Let's see, I'll use a black pen for the coordinates. And what are my angles here? Oh, you know what? I'm going to extend this a little bit. Extend this. All right, so this is, remember down here it's 30 degrees, so up here it's 30 degrees. This thing in here is 60 degrees, right? Because instantaneously, these are perpendicular. You've got the radial and the theta velocity. So this is a 90-degree triangle here, this one. And since this is 30, this is 60. And that makes this 60 as well. I don't even remember which angle I need anymore. Let's see, that's V theta. Oh, and this is point B. Right, point B. So let's look at the different components of velocity we have. Acceleration of point B. Let's see. You know what? I'm trying to remember if I forgot to add a question in this. We want the, oh, this is still part A. Geez, guys, I'm sorry. This is a this is the vector. We got to figure out the actual velocity. I'm like, what am I doing here? Yeah. All right. VR cosine 30 plus, because we got to figure out the magnitude. V theta cosine theta. So these are all, these are each of the vector components, right, of the velocities at point B. I don't know why I put B here. I confused myself. And then the Y component, let's go over this just real quick. The X component, we've got VR cosine 30, right, this component here. This should be, you know, I'm going to put a little Vx in here and a Vy. That way it's not confusing. This is not X, the coordinate X, right? This is the velocity in the X direction. Plus we've got V theta, right? Cosine, oh, that should be a 60. 60. So here's our 60 degrees, right? The X component of theta, V theta, is here. And then the Y components, we're going to have, let's see, VR sine 30, right? So that's just this downward component. And then we've got V theta sine 60, right? This, well, the downward component of phi theta. Now, notice here I don't have any signs in here yet, because those signs are taken into account up here, right? This is VR and this is V theta. So all I'm doing is I'm converting this into X and Y coordinate system. So now what I'm going to do is I'm going to actually work out some of these, so Vx. So I'm going to plug in the numbers now. Yeah, I had forgotten I did this when I negative 0.2 cosine 30. Because even though you work it out in polar coordinates, right, to get some sort of magnitude of velocity, you need to still put this back into some kind of a, XY system. So we've got negative 0.2 cosine 30 plus, what do I have? I have a plus of a minus. Oh, you know what? I think I was supposed to make that a minus up there. Let me see here. What's going on? 0.48 cosine 60. Let me just do a quick calculation here. Oh, yeah. We're doing all right. So notice here, I have to look at this now and say, okay, what does this mean in XY coordinates, right? So the V theta is negative, but the X component is going to be positive, right? So this is the problem. You have to sit here, well, not the problem, but this is where looking and understanding the direction comes into play, right? The X component of VR is negative. The X component of V theta is positive. So I'm going to use a positive 0.48, right? Even though E theta, right, in the theta is negative 0.48, right? That results in an X component that's still positive. It's your Y component that's going to be negative. So that's what you have there. And here you wind up with, let's see, 0.0668 meters per second. And let's work on Vy. So I want to make sure you followed that. Well, let's do the Vy and then I'll review it. So Vy, the Y component of this velocity, right, is negative. So I'm gonna write this in here. I'm gonna have a negative 0.2. Again, maybe I should have pulled the negative out to show you the sine 30, right? And then I've got a plus. This time I have a negative, right, 0.48 sine 60, and this equals negative 0.51. It looks like a 6. So all I'm doing here is I'm looking at polar coordinates and I'm saying, okay, I've got a velocity in polar coordinates that I'm going to now convert into, so I can figure out the velocity in XY space, right? I'm going to convert this into XY space, and I draw the vectors out in polar coordinates, right? Remember, these are instantaneous vectors. So I know they're acting perpendicular to each other, and now I break down and I get the X and Y components of these, right? These vectors. But these vectors, or these signs up here, denote the direction of the vector in R and theta space. Now that I've drawn them out in XY space, right, I now have to be conscious of, okay, these are the magnitudes of those, but what are the directions in XY space, right? So we have to change our thinking from one coordinate system to the other. So now you have the sum of these things, right, is you've got 0. Well, you know what? I'm going to put Vx here, and I'm going to put Vy here. Right, because this is what they look like. Your X is a positive, your y is a negative. This is your resultant. And let's call this angle, since we've been using theta a lot, let's just use phi here, right? So VB, the magnitude of it is just the square root of the sum of the squares of 0.0668 squared plus 0.516 squared. And then phi, right, is the inverse tangent of, what do we got? 0.516 over 0.0668. So now you've got VB. Once you plug and chug these numbers, right, 0.520 meters per second, and it acts at an angle, or it's acting at an angle of, this turns out to be 82.6 degrees. So I will be more specific than the book on this, because the velocity at point B is kind of misleading. I can see where people would stop at this point, but we want to know the the actual velocity, right, which is 0.520 meters per second. So all we did here is we chose the most convenient system for this problem, which is polar coordinates, right? We got the information. I mean, if you try to do this in XY coordinate system, you've got to deal with you got to deal with all these vectors again. It's just a little easier to put it in the polar coordinate system, use that, and then you've got your polar coordinate vectors, right? ER and E theta, and then you, now notice this is a fairly simple problem, right? If you had some acceleration, well, if you had more functional terms, right, you would have had to, function of time, you would have had to evaluate them appropriately. But let's see, now we're at part B here. Right? Do I have a second page for this? Hold on a second, I think I'm missing the page for something. Oh man, I think I did. I think I forgot. Let's see. All right, for this one, I'm going to take. Let's draw this out. Part B, we've got acceleration. I'm going to rewrite the equation just because it's r double dot minus r theta dot squared er plus r theta double dot plus 2r dot theta dot e theta. Let's see. Go back to these terms. We know from above this term, right, the acceleration in the r direction is 0. This is from part A. And the acceleration in the theta direction is also 0. And we write this out. Everything else we have values for. So I'm going to fill in the values just so you can see. Right, acceleration is just going to be, we've got a negative, and we've got a 6 times negative 0.08 squared. This is your r component, plus, we got 0 here, and then we're going to have 2. This is r dot, right? So this is a negative 0.02 times theta dot, which is a negative 0.08. And this is E theta. All right, so this winds up giving us an acceleration vector equal to negative 0.0384 ER plus 0.0032 E theta meters per second squared. So this is the acceleration vector. Now we do a similar drawing, and in fact, let's look at, I'm going to have to get a second page. So I don't have this in my notes, so let me grab another piece of paper. Oh, come on. Oh, get it from the notebook. So let's see how many mistakes I can make on this. All right. Find them. Let me draw the same triangle, basically. Well, you know what? Maybe I'll start on a separate sheet of paper. Sample problem 1120, spring 2021. All right, so let me draw this out. So for the acceleration vector, we have the same thing going on. We've got in the r direction, we've also got a negative acceleration. And then in the theta direction, we've got a positive. Oh, so this, I didn't leave myself enough room. But notice it's very small. Look at the value of that, 0.0032. So this is acceleration theta, right? So now let's draw our coordinate system here. X, extend this again. So this is still also 30 degrees, right? And what do we got? This is a 90-degree triangle, so this is 30, 60. And then we've got another, let's see, this should be another 30 degrees here. Right, because this is also 90 degree. So you can see this is, well, up here it's 60 degrees. This should be enough information to, let's see, X and Y. This is also point B. Right. All right, so let's look at the acceleration in the X components of acceleration, right? Oops. Are going to be pretty much the same as what we got for the X components of velocity, in terms of sine and cosine. And so we've got the R acceleration, right, times cosine of 30, right? And note this is this will be a negative when we put the number. I'm gonna, let's see, what am I gonna do here? It's already a negative. I'm gonna leave the negative. I'll leave this as AR right now. And then we've got A theta, which is this way. I don't know, I put the label over there. So now the X component of A theta is going to be sine 30, right? Because that's pointing this way and it's opposite over hypotenuse. And then the Y components of all these, again, it's going to be the same down here. We're going to have AR, we're going to have sine 30. Oops. And then for A theta, right, the Y component is pointing upwards. So you could use sine 60 or cosine 30, right? So let's put some numbers in on these. All right, AX, we've got the R component. Let me move this down. Oh, you can see it. Let me stick this underneath. We've already got the negative 0.0384 sine 30. And we're going to have a plus. Now, the acceleration for theta in the x direction, right, that is also negative. So I'm going to write in the negative here, negative 0.0032 sine. Oh, wait, I messed up. You guys are supposed to catch me here. That's cosine 30. This is sine 30. Cosine, yes, cosine. All right, so this is going to give us what? Let me solve this because I don't have it solved. We got negative 0.0384 cosine 30. And then we've got negative 0.0032, well, times a half, right? Plus that last part. So this gives us a negative 0.034. I'm going to round here, 349. Again, this is a very, very small term, right? So you can see it's not, maybe it's an order of magnitude smaller than that one. So it doesn't really affect the final term that much. Now for the y acceleration, we've got the same, well, not the same thing. We've got a similar situation we got to look at. The r component is still, let's see, for y, it's still negative, right? So we're going to have negative 0.0384 sine 30 plus, now, the theta component in the y direction is positive, so I'm going to use the positive value. Cosine 30. All right, let me put these numbers in here. 0.0032 cosine 30 minus 0.0384 sine 30. This gives me a negative 0.01. How many decimals did I go here? 6.444. I really should round to 3 meters per second squared. Anyway, we'll round at the end. So now we got this acceleration vector that looks like this, right? We've got AX, which is actually fairly small. And AY is actually smaller. So AY goes like this. And we've got our resultant. Oh, and let me put another angle in here. Let's call this angle phi again. Right, so AB is equal to the sum of the squares, or the square of the sum of the squares. I'm going to leave out the negative signs for clarity here, or room. Zero, 164 squared. Let me do this number on my calculator. Sorry, guys, I apparently didn't finish the notes for this problem, so I have to do it right here. 0.0349 squared plus 0.0164 squared, square root of that. So if you do find a mathematical error, let me know. 0.0386 meters per second squared. Oh, I forgot to report. So phi is going to be the inverse tangent of what? We've got AY over AX. Oh, I don't know why. So it's the inverse tangent of Where's AY? The negative signs are going to cancel, so I'm just going to write them 0.0164 over 0.0349. And this gives us, let's see, inverse tangent. I hope I'm in degree mode here. Yes, I was showing another class how if you're not in degree mode, you get some weird numbers. And 0.034, well, it worked earlier, so let's see, 0.0164, 0349. Inverse tangent gives us 25 point, we'll just go with 2 degrees. So acceleration of B is 0.0386 meters per second squared at an angle of, and what's our angle? Our angle is with this respect to the horizontal. All right, does this make sense? So this is a good double check, considering also that I just did it on the fly here. How am I going to do this? Think about this. Let's think about the way this thing's moving, right? This thing is moving. It's moving sort of in the theta direction. It's creating a circle arc, right, this way. Plus, it's also moving in this way, right? Acceleration is always pointed towards the the center of the instantaneous diameter, right? So that makes sense that acceleration of B is pointed in towards the center of the arc. And it also makes sense that the theta we're experiencing, the acceleration theta, is this 25.2. Is actually slightly less than the direction, just because we're also moving in the radial direction inward, right? So we're moving, we've got VR and V theta, right? It looks like this. So this also has a component that's contributing to that. Well, it's primarily a result of the theta, but you can see, you know, it makes sense. It's pointing down 25.2 degrees, sort of towards the center of that arc of rotation. All right, that was a longer problem than I expected. I had forgotten, when I looked at it, I'm like, oh yeah, it fits on one page. I had forgotten that I didn't have the rest of it written out. So I only went up to here in my notes where I gave you the vector. I don't know, maybe last year I had them solve it on their own. I ran out of time or something. But anyway, this is the acceleration of B, and this is the velocity of B. Those are the magnitudes with their resultant directional components or angles. Are there any specific questions about this problem? Every time I think I glance at the problem, every time I think, oh yeah, I know what I'm explaining, I always wind up running into trouble. Okay, so if there's no questions on that, let me, this is the end of chapter 11. Let me just make a comment about homework, since most people are here now. Are most people here? Oh, yeah, here's the, okay. So homework. I went into McGraw-Hill the other day. I looked at how many people were doing the homework, and I don't know if anyone's actually started the first homework. Let me see. This will tell me, I won't pull up any names here. Oh, yeah, that's right. One person submitted it. 4 people are in progress. Now, what's interesting about this is there's 5 students listed as having accessed the McGraw-Hill Connect site for this class. Now, just looking at the roster, there's 8 people, so we're missing some people. And I don't know, I'm not going to say any names. I don't know who they are because I haven't looked at them yet. I'd have to click on this and see them. But if you haven't started the homework, go start the homework. So I don't know, in all three of the classes, I'm using the McGraw-Hill site for homework. I know there's a lot of homework. That's really the only way you can learn this stuff well, to actually be able to do it quick enough, when it comes to, say, doing it on a test, or using what you know in subsequent classes, right? So if a subsequent class is calling on you to do, something in polar coordinates, you need to be able to, look at those formulas and figure out, oh yeah, this is what I'm doing, right? So it's not just enough to listen to me and watch me do the problems. You have to do the homework. And that's why the homework is such a, 40% of the grade? I mean, it's a pretty big proportion of the grade, just because, and that's always been true for any engineering class. The homework is a significant portion of the learning that goes on in these classes. So make sure you do the homework. I don't think I'm going to start chapter 8 right now, just because we're almost at the end of class. That took longer than I thought. But I do want you to know the chapter 8 material is pretty quick to go through. All I did, let me just show you real quick. If you're going to print the slides, don't print. I don't know if you've been printing or not. A lot of people just download them. I think it's really only the first, let's see, yeah, the first 12 slides, and then not even the last or the first one here, just because the bulk of the material that I want to get through is all in here. So this should be relatively quick. I've got a few example problems to do. Where are all the example problems? So we'll cover friction on, we'll start with this. Again, this is chapter 8 material, which technically is statics, but when we go into chapter 12 and start writing force balances, we're actually going to have to start accounting for things like friction. So I want to make sure we've covered it. You probably covered it in physics, but I do know your physics last year was awfully truncated. So I'm not sure how much you remember. So I want to make sure I get through friction. We'll do that on, what's today? We'll do that on Friday. I don't know why I said Wednesday. Today's Wednesday. We'll do that on Friday. All right, so that's what I have.